Please be sure to be logged onto the webinar through your own individual connection. We require you to be logged on through your own email or connection so that we can accurately approve attendance in the event that you or Half Moon is audited by any licensing board. We also require individual connections so that you can access the quiz at the end of the webinar. The quiz will automatically appear on your computer screen in your default internet browser after I end the webinar today. If for some reason the quiz errors out or you're not able to successfully submit the quiz, you can always access the quiz via the thank you or follow-up email, which is sent about an hour after the webinar has ended. Everyone will receive this follow-up email, and it's not indicative of a failed quiz submission. It's just in case you weren't able to access or finish the quiz after the webinar ended. Certificates will be issued for today's webinar. If you did not successfully submit the quiz after attending the webinar, please be sure to do so through the thank you or follow-up email afterwards. The certificates will be sent via email in PDF form and will be sent by next Wednesday, July 5th. If you need your certificate sooner for relicensing purposes, you can reply back to hmn@halfmoonseminars.org, or you can always call into our office to let us know. We will be taking questions throughout today's webinar. If you have a question for Mr. Cromer, you can ask your question in the questions area of the GoToWebinar panel on the right-hand side of your computer screen. Materials for today's webinar were sent via email. If you weren't able to receive the materials, you can always access them in the handout section of the GoToWebinar panel on the right-hand side of your computer screen. Once you click on the PDF, the document will open in your default internet browser where you can view, download, or print it. And with that, I'll hand it over to Mr. John Ross Cromer, Master Electrician, Mechanical Engineer, and Certified Photovoltaic Installation Professional.
All right, good morning everyone, or afternoon if you are on the East Coast. Welcome to our battery program. I'm actually actively working on my first kind of solo battery project. Actually, when I got into the solar industry in 2008, my very first project was a battery project, and while batteries were not cost effective, this was for a grid-connected home, and the homeowner wanted a source of backup power, but they did not want to have a gas generator on their property for whatever reason. And so they spent more money to have less power with some batteries. And then for the past decade or so, every project since then has been batteryless because batteries are expensive. And most customers, when they go solar, they want an economic payback. And so you get into the cost of batteries, and that usually makes the project non-economic from a simple payback perspective, but perhaps there's some value that isn't being modeled into the equation. What's exciting today is that the battery market is heating up. You know, in 2008, 2009, the solar industry was experiencing triple-digit growth, and right now the battery industry in 2016 it grew by 126%. So the battery industry is really exciting. There's a lot of growth in it, and as I get further into my residential off-grid design, I'm learning more about batteries myself, and I think that many solar projects, if not every solar project moving forward, should strongly consider batteries, and particularly in certain markets like commercial solar, there are huge applications for batteries that might result in more cost-effective systems than we've ever seen before in terms of unsubsidized solar economics. So we're going to talk about all those topics today. It's a pretty dense class. I've actually revised the program a little bit, and so I've included the Dropbox link to the PDF for the course slides. But we'll figure all that stuff out as we go along. So with that, let's get into the program material. All right, so I think that the most fascinating thing about batteries are the applications for batteries in the commercial solar market. Now, a lot of utilities are doing utility scale battery projects that are kind of like experiments to get familiar with the technology. They're not that large of battery banks compared to what we need, but utilities want to be a little bit ahead of the game. Actually, some utility regulations for deregulated grids can kind of prevent utilities from doing batteries, because on deregulated grids, the utility is not able, like if you own an energy generation device, you're not able to sell the electricity or be the distributor of the electricity. And with batteries, it makes people rethink how they use electricity and what the rate structures are. So anyway, I'm sure most of you are interested in batteries for residential purposes. And we're going to talk about the nuances of residential design for much of the rest of the program. But what I wanted to point out is in other classes, we cover billing structures for electricity, and we discover that billing structures for residential are volumetric in the sense that, let me change my pen color here to something more vibrant. But this curve, this chart is kilowatts in power and hours of the day. So the volume under the curve is the kilowatt hour. And so we as consumers are billed for the total volume under this curve. It's how many kilowatt hours did you consume at the end of the month, and that is your electric bill. And so solar depletes our kilowatt hour usage by as much as we kind of generate in the middle of the day. And then sometimes there's an inflow from the grid, and sometimes there's an outflow onto the grid, and how you're compensated depends on your net metering policy, and all that stuff you should be familiar with if you've taken any of our more introductory programs. Commercial businesses are billed by this maximum height of the curve. So it's not volumetric, it's linear. It's how much, what is your maximum power draw at the end of the month? And your maximum 15-minute or 30-minute power draw at the end of the month, that number, whatever your maximum was, that number can comprise, in some cases, 75% of your commercial client's electric bill, and often it's more like 50-50, sometimes it's 25-75, but as a reasonable assumption, you can assume at least half of a commercial client's electric bill does not come from the volume under the curve, but instead comes from this maximum amplitude. And of course, the problem with solar is it generates all this demand energy in the middle of the day. But in terms of demand savings, all it does is, here's your new maximum. That's like at 5 p.m. when the sun, begins to set, but your business is still open. So all it does is you're not reducing your demand by, the size of your solar array. Under kind of a best case scenario, all you're doing is pushing your max demand from high noon over to like 5 p.m. and that difference is your demand savings, or not. A cloud could come and sit on top of your solar array on a partly cloudy day, and your building demand could be pretty close to what it would be on a fully sunny day. And so on that one partly cloudy day, you might miss the production window for demand savings. There might not be any. The solar array might be turned off. And so then there's no demand savings. And if that's half of a commercial electric bill, then solar for commercial clients generates at half what it does for residential. Now, commercial has some advantages. One is economies of scale. So you can do a really large solar project and get the price down that way. But without a good rate structure for solar, what we have is a case where commercial businesses are being billed for their peak demand, and we have solar producing at demand times, but the client's receiving no compensation for that. And what batteries can do is you can go and install not a battery bank that'll run the whole building off grid for a couple of days, not even a battery bank that'll run the building off grid for 8 hours. You know, we're not trying to run the building, the battery, for the entire day. Instead, we're trying to run the battery for just a short, maybe a half an hour, maybe a 2-hour window, and maybe not every day, maybe only a couple of days a month during peak times. And that's the most valuable time for the battery bank to run, and that's really where the utility makes the majority of their total profits, comes from this demand rate structure for businesses. And so what's fascinating about batteries and solar is that as battery prices drop, and you take a look at your demand charge, it might be that a solar array doesn't make any economic sense at all. Or it might be that a battery bank that runs a building the entire day for demand management doesn't make any sense at all. But the combination of a small battery and then a right-sized solar array can actually provide demand management and result in saving the client more money than their retail price, because they're generating electricity at the peak times of day. And it's kind of ironic because in many states across the country, utilities have proposed demand management structures for residential customers in an effort to stop revenue loss from the solar industry. And what I think is neat is that it actually might be in the era of cheap batteries that a demand rate structure is the most financially beneficial structure for a solar customer, because let's face it, you know, a solar customer doesn't want to have a system that turns off in an emergency. They want to have their solar array produce, you know, backup power. So, you know, it's almost the inverse case where a residential customer does not have a very good rate structure for taking advantage of battery economics, whereas commercial customers have a rate structure that's perfect for battery economics, that's custom fit for battery economics. They would love to do load leveling. They would love to do load leveling with gas generators, but they're not allowed to. They'd love to load level with batteries. The problem is batteries are expensive. Well, if all of that suddenly changes overnight, then every business is going to want to run out and do batteries and solar. And I think that that'll be the fastest growing market segment for a while, simply because it's been, they haven't had the right policy to bring solar to flat commercial rooftops, but now they have the technology, or at least the technology is coming to market. So anyway, and that's simply, you know, there are rate structures for residential customers, like time of use rate structures, where, you know, you can buy low, you know, during off-peak times and then sell high during on-peak times. But the problem with this rate structure is that if you're using a battery, you know, something like the Tesla Powerwall or a longer lasting, higher quality lead acid battery bank, that's going to run you around 16 cents a kilowatt hour over the total life of the battery bank. So this differential between buying low and selling high, it really has to exceed 16 cents in order for the battery, in order for this process to even be economic. And it really needs to be about double that in order for people to go out and buy a battery that's going to last for 10 years and see a payback in a time frame that they're happy with. Otherwise, they won't do it. And the problem with the concept of buying low and selling high, you know, charging your battery during off-peak times and discharging it during peak times, you know, with an electric vehicle, that's all right because you've already bought the battery and you've already committed to using your electric vehicle. You're going to use it. You might as well have a good rate structure for charging. But in terms of day trading electricity and just buying a battery to do explicitly that, you know, then we get into the fact that these off-peak periods are not available year-round. But this whole time variable schedule, every time I log in to GoToWebinar, I forget to close my Gmail, and then my phone calls me through all that. So let me take care of that. Sorry about that. So the point of all this is to say that, you know, your time of use metering residential rate structures are not always available to the customer. Often they're only available 4 months out of the year, so you don't even have that differential available year-round. And so if you need a year-round cost savings daily opportunity of about a 32 cent a kilowatt hour differential between your off-peak rate and your on-peak rate, so that needs to be, in my opinion, it needs to be about 32 cents a kilowatt hour difference in order for just uneconomic residential batteries to come to market. And this differential does not exist in almost any United States market. The exceptions being maybe in New York City and in around San Francisco, and also in Hawaii. In Hawaii, just everyone, the average retail price of electricity is above 35 cents a kilowatt hour, and that's in the most populated areas, and then it goes sky high from there. They have so much solar in Hawaii that solar array owners are not allowed to export power onto the grid. And so in Hawaii, it's economic when you're saving 32 cents a kilowatt hour or more, it's economic to go buy batteries and charge them with solar instead of losing that energy or, you know, not, or buying it from the grid at a later point in time. So there are markets where uneconomic, unsubsidized battery economics do make sense, just not in the U.S. right now because we have relatively lower prices of electricity. And I think the most interesting, you know, kind of in the United States rate structure for taking economic advantage of batteries is the commercial market. And for that reason, I've kind of landed on a design philosophy for batteries, which is you really do economic projects for the commercial market. And then when you get into residential batteries, it's more of a, well, this is the price of the system and it has a 10-year payback, and then for an extra $8,000 we can enable the system to provide backup power during a storm, but just a little bit. And we're going to talk about that. You know, you try and talk the customer into getting a backup generator. Then again, during an emergency, you don't need a whole house worth of power. You might just need a little bit of emergency power, given that during the day you have all the energy you want. Anyway, so that economically, you start to need granular data. And so that's where service panel monitoring, you know, you might, it's kind of important to have every bit of information related to your building consumption and the energy going into your battery bank, and also perhaps the energy that could possibly be supplied by the solar array, so that you can have smart electronics that will operate, you know, when you have surplus electricity and then turn off don't. And so we talked about how service panel monitors and other classes can be used to clamp around the circuits in your circuit box and monitor the current for your kind of on-site energy system. Or alternately, you could stay within the same product manufacturer. Monitoring for battery systems is much more complicated than monitoring for a regular solar array. When you monitor for a regular solar array, it's just your inverter is tracking the energy out of it. It doesn't have to be exactly accurate. If the inverter goes on the blink, usually there's not too much diagnostics that goes on because the system's relatively simple, so you can just kind of, if you're a solar installer, you can just kind of figure out what's wrong and fix it. Battery systems are much more complex. And so the battery monitoring systems will monitor temperature, cycling, the energy that goes through every step of the process from the solar array to the batteries to the load. So you have energy from the solar array going into a charge controller, energy from the charge controller going into the battery. So you might monitor energy into the battery, energy out from the battery. You also might have relays set up for load dumping or shedding, where you might have an auxiliary load such as a heater. So you might have a floor heater in your battery room in the wintertime, and whenever the solar array is producing excess energy, you turn on a contact relay and start heating up the room that the batteries are stored in, which is better for the batteries during the winter. Or you could even have load or line shedding, where you put the inverter in the garage and then you wire a critical load panel up to the inverter, and so when the power goes out, your whole house loses power, but the critical loads remain on. And I don't really like that philosophy. I think, hey, you might as well try and power the whole house. The reason is, in the middle of the day, you can power the whole house. It's just at night you have to be careful. So I would prefer kind of not doing critical loads and making the home smarter, but it really depends on your application. Sometimes critical loads are great and desirable. So the theme is that solar design is very simple. It's a couple of circuits from the solar array going into your inverter. We've seen in other classes either commercial software or string sizing software will do that for you. There's manufacturer provided software that will do the racking, balance of system design. We've even seen some commercial software that'll spec out the balance of system material, or at least get you on your way there. And we've seen with the inverter itself, you can either wire it to the load side of your service panel or come out the other side of the main breaker but before the meter and land on the line side, either way. And the inverter just has simple internet monitoring integrated into it. And that's all not that big a deal to figure out. But when you get into battery systems, now you have these advanced monitors, and maybe you don't need all of the functionality, but it's there and you have to pay for it. I've gotten into looking at generator auto start functionality, where most of these battery inverters will have either integrated into it or as an add-on a generator auto start relay or function or circuit, where you wire it up to a generator and it turns the generator on or off. The problem is not all generators can turn on and then back off. And so, when you get into that, it's, well, is my generator compatible, or what is my generator and what's my purpose of the generator? If I'm building an off-grid cabin, and I'm trying to do it really cheap, I might use the cheapest battery inverter I can find that can just turn a generator on and have a small transportable hand crank gas generator there with a simple auto start function, and it turns the generator on and it just runs until it's out of gas. And that might just be a simple solution. When you need to run a generator, your batteries, they're low anyway. So the small generator, one tank of gas, it might be burned very efficiently. I don't know. It depends on budget and it depends on application. But these components can get very expensive. So like advanced algorithms, your battery inverters are set up for multiple modes. Like in Hawaii, the inverters have a mode that would be for zero export. And so when the zero export mode is enabled, the inverter senses when the building is drawing more current than or pushing out more current than what it should, and it curtails your power production to stop that export from happening. Then there's an off-grid mode, and there's also modes where, for like what we said with load shaving for commercial and a variety of other kind of niche market configurations for the same inverter system. But none of that stuff you're going to find in a traditional batteryless inverter. And so, batteryless inverters, a good quality batteryless inverter system, whether it's a high quality string inverter with a rapid shutdown disconnect box or a SolarEdge DC optimizer system with module level panel electronics, those are all going to run you around 30 cents a watt, whereas the battery system and components are closer to 60, 65 cents a watt, and that's kind of with doing larger projects. It can be more expensive on smaller projects. So you're essentially doubling your inverter budget when you decide to go with a battery inverter, and then you're adding the cost of the batteries and the cost of the wiring and labor involved. Other things involved in the design, we may have a solar array going through a charge controller into the batteries. You may instead just have the batteries kind of on their own inverter, and usually you might have multiple inverters, and the battery inverter is the master inverter, and there's no charge controller, and now you have a second inverter that the solar array is tied into, and the master inverter can drive the slave inverter. So it's called a master-slave electronic configuration, where you have kind of redundant systems and one drives the other. And so why might you have that? Why might you have two inverters instead of one inverter? Well, I'm doing an off-grid system, and I want my client to have two battery inverters because, if one fails, I want them to be able to use the other one. I don't want them to run out of power. So I like a little bit of redundancy in the design, if not a lot of redundancy. I think a little redundancy is good. Too much redundancy can be unnecessarily complicated. Another reason, perhaps even more popular, is the solar customer may currently just have this and not have the charge controllers and the fancy equipment, but they may just have that traditional batteryless solar array sitting on their rooftop. And so the question is, well, can you retrofit a battery bank onto this array? And the best way to do a retrofit is to put a this is just a regular solar inverter, is to go and you get a battery inverter and then you wire it up to your battery bank. Here's their battery bank here, and you just have them operate right next to each other in parallel. And you say, well, is this possible, and do we need to worry about backflow issues and stuff like that? And the answer is no. So we have these solar inverters that are on the homes already are listed per the UL to detect grid failure and then to shut off if there's a grid failure. And by putting this whole system on, say, a transfer switch and having your batteries right next to it, now you're running off the master battery inverter. And if the batteries fill all the way up, if they're fully charged, and the solar array is sending too much power back at that time, what will happen is the battery master inverter will sense that, since it's monitoring the battery bank, and then send a grid failure signal through the power line to the solar inverter and shut off the solar array. And so now all of a sudden you're running off your batteries in the middle of the day while it's sunny outside, but just enough to run your batteries down a little bit and then to charge it back up. You know, it's okay to do that. Now, what's even better is if you don't need to do that, is if the master battery inverter can actually send a control signal and curtail the solar power. So if it's monitoring your building energy demand and it's monitoring your solar array and your battery level, it can say, hey, your solar array is 10 kilowatts, but we only need 5 kilowatts. And it'll turn off half of your solar array, but that way it doesn't have to turn off the entire solar array. And you might gain a little bit of battery life by having that advanced functionality. So if you already have an in-phase array, you might want to look for an in-phase battery. If you already have a solar edge array or an SMA array, you might want to look for a solar edge or SMA battery, just to take advantage of that smidgen of system elegance. But the truth of the matter is, even without that elegance, the case where you're running on your batteries in the middle of the day because the sun is up, that's a very rare circumstance, where usually if your batteries are fully charged and your solar array is at full power, you're just running your batteries in the top range of their cycle, which is okay for it's okay. You are using your batteries, but we need to get a little bit further into battery specifications to understand how deep cycling impacts battery life. All right, so with off-grid systems, we have a couple of different options. We have our solar array going into our battery bank, and often this is on a shared kind of DC bus. And so what happens is when your batteries are full and you're grid connected, any surplus power from the array simply gets sold back to the grid. And that's desirable and preferable. You know, you really don't want to use your battery if you don't have to. And as we talked about previously, buying low and selling high, you're not going to break the stock market by doing that because of the cost of running the battery. Batteries, as discussed, are getting smarter in that they can control generators on and off. And that's kind of interesting because normally when a generator is running and it's powering your house, it's generating a surplus amount of power. Well, now that surplus amount of power can go into your batteries and be recaptured. And what that means is, you don't have to crush it with your generator, and often we'll see generators that are 25 kilowatts or more. You know, it might be that with a energy efficient home, you get away with a 15 kilowatt generator that is efficiently powering the home, and whatever surplus power is using to recharge the batteries back up. And we'll talk about sizing in a minute. Battery architecture then becomes pretty complicated, or it can be. I think of it more as flexible, because you can have a battery system operating in parallel with a battery-less system. The battery inverter manufacturers are a little bit wary of having battery inverters operate in parallel with other battery inverters, particularly if they're not the same manufacturer, if they're not on an integrated communication system. But in terms of kind of your dumb battery-less inverters combined with your single battery inverter, you can have plenty of solar added on and then plop on one battery inverter and make your system storage capable. If you want to expand your array, you could also buy a charge controller and wire it directly to the DC bus that the battery bank is on. And the charge controller, as you can see here, it kind of accomplishes a similar thing as the string inverter in that it just regulates the electricity from the solar array into the load. It's just that it's a DC load instead of an AC load. It hasn't gone through a complete inversion process yet. So this results in, it's kind of fun, because battery-less solar design has become all one size fits all. It's just, there's your roof, do as much solar as you can. You know, here's your inverter. The inverter can hold this many panels. It's become kind of automated. But battery inverters, there's actually, you know, more system architecture to know about and design with. For that matter, your design software is not as available for battery-less design. So like Aurora and Helioscope, they don't really do battery-less or battery bank designed. And you know, Solar Design Tool does what it can in terms of they have the battery inverters put into their system so you can do string sizing, but they don't have any assistance with charge controllers or the batteries themselves. In terms of your design software for batteries, there's 3 resources that I'm aware of out there. 2 of them are free, and they're kind of the same. The Homer and the System Advisor model. These are both kind of projects funded through the Department of Energy. The System Advisor model in particular is put out by NREL, and it's kind of like PV Watts on steroids. So in other classes, we get more in depth into PV Watts and how to extract hourly data and weather data from PV Watts. NREL will actually take your load data and your PV Watts data and kind of simulate some battery cycling, but they don't use a very advanced method for that. So some installers really like the System Advisor model, but I think the learning curve is pretty steep, and so generally that's when you make the transition into commercial design software, but that doesn't get you anywhere closer to battery-based design. So then lastly, we get into Energy Toolbase, and I think that in terms of battery design, Energy Toolbase is one of the more advanced softwares out there. It's just the caveat is it's only good for commercial demand management. It doesn't do off-grid modeling very well. It will do some economic analysis for residential time of use metering, but they're pretty much exclusively focused on optimizing the economics in terms of what's right sizing between your array and your battery bank for commercial demand rate structures. But if that's your market niche, it's a great software to check out. We talked about the different communication systems. We're gonna take our break at 1/4 till, so we're gonna take our break in 5 minutes. The Desire website, we've seen this in other classes. It's a website you can use to check out all different green energy incentives. It's a little bit difficult to check out battery incentives on the Desire website. There are some incentives out there. California gives you an incentive that's about 30% of your battery bank cost. Let's see, New York will give, I'm not sure if it's available for residential customers. I think for residential customers they give like $1,000 to, and then commercial customers they actually will give an additional $50,000 of comprehensive green building incentive budget for doing a battery bank. And that's almost like if your solar projects are cheap enough, and they usually are in New York, it's very economic for the client. And then I think Delaware is considering a storage tax credit, but it's limited to like $3 million, which is only like 50 battery projects. So if you're in Delaware and you really want that battery tax credit, you got to start preparing your applications. I'm sure it'll be competitive. Other general notes on batteries, and then after the break we'll get into spec sheets and sizing discussions. One interesting play lately, the solar leasing market has become less popular. So this chart is a little out of date, but it kind of looks like this, where as the cost of solar has come down and as some customers have gotten familiar with the downsides of solar leasing, and as more, perhaps most importantly, conventional financing comes to market, the popularity of solar ownership is now larger than the popularity of solar leasing. But batteries may be one market where a solar leasing company like SolarCity has a competitive advantage. Because if a utility can log into your battery bank and run it during demand times, they see similar cost savings to what those commercial businesses do. And so they might be able to pay you, 50 cents a kilowatt hour for the use of your battery bank. And that might be worth it to the project owner, but the utility doesn't want to have to deal with 50,000 different customers with their own individual battery banks. It's a lot easier to deal with one solar leasing company. And so maybe there's a competitive play that SolarCity or Vivint could use on batteries, where if you're one operator and you have control over a large number of distributed batteries, you might be able to better negotiate a battery incentive with the utility than otherwise. And power outages are increasing for a variety of reasons. So whenever there is a major power outage emergency like Hurricane Sandy, the interest in batteries goes up. And really, shouldn't it be the other way around? shouldn't you have the battery capability when you really need it? So hopefully when we get into kind of the design phase after the break, we'll demystify that process. So right before the break, let's think about something for a minute. Many customers want to go off-grid with their batteries. And, especially solar customers. Solar customers feel a little bit discriminated against when their like net metering policies change or something like that. They say, well, we're trying to, we're putting in our own money to help the environment, and we're the ones who are getting a 10-year, 12-year payback, which is not what most investors would do. So, why are you making it harder on us to help clean up the electric grid? Well, utilities have their own counter arguments that are reasonable too. So eventually, the utility will say, we want to pass a policy to stop the revenue loss from solar customers to make sure that they're paying their fair share. And then that might be a solar discriminatory fee that only applies to solar customers. It might be a minimum bill requirement where they have to pay a certain minimum amount. And most customers, like I live inside the city, and I pay $15 a month for my grid access fee. But if I go out into the countryside on the rural co-op, that grid access fee jumps up to $30. When you think about it, you are buying $30 of infrastructure cost every month before you purchase a dime of electricity. And so you might say, well, I don't want to pay this, especially if the utility is trying to pay me more money. I'm going to go off grid and not have a power bill entirely. Well, $30 a month over a 10-year period is only $3,000. And maybe a battery bank that can run a typical family of 4 residential home, that battery bank might cost, just as a starting point, $25,000 and have about a 10-year life. And so you're never going to make a payback by cutting the cord. It's just the meter fees would have to be $300 a month in order for that to start making sense. So again, it's maybe a residential customer that already has grid access. Maybe they should just take advantage of that and do a small battery bank. Normally they have the grid, but during emergencies they can use their solar array, and a small battery gets them there. However, my client in Mississippi, he owns a few acres of land, and he wants to build way back into his property over a creek and et cetera. And the power company said, well, we're going to charge you, $20,000 to bring power out to your property. And so he looks at the new construction costs and the meter fees and the fact that this particular utility has kind of recently adopted an anti-solar stance. And he says, well, I'm doing the solar array anyway, so I'm just going to not connect to the grid. And I'll whatever money I'd spend on grid access, I'm going to dump into my batteries, and maybe I have to replace them 15 years down the road, but we'll see what the battery market looks like at that time. I think that's a warning to utilities where, sure, it's not going to make sense for most solar customers to cut the cord if the cord is already there, but even if they end up spending a little bit more money, solar customers definitely have that drive to be off grid. I mean, my conversation with this customer went, well, it would be cheaper to do a smaller solar array and bring the power out to your property and do a small battery bank. And that way you do solar and batteries, but you have the reliability of the grid access there. And he says, well, I want to do off-grid. I say, well, actually, off-grid, if you run out of power, you're completely out of power. And so, yeah, we do have a generator and we have a well-sized solar array and we're doubly redundant. But you realize that if you're out of gas and you're out of solar and you don't have electricity, you might have wished that you had that hardcore power line. And he says, I just don't want to deal with them. So solar customers, in other words, many solar customers have deeper pockets than the average American, and they will spend a little bit more money in order to cut the cord it may not make the most economic sense, but there is that drive. So in our case, the client was faced all with a total life cycle cost analysis that showed him that even though he was spending 20 grand on grid expansion fees, that was the more economic option than spending the same amount of money on a battery bank. And he went with the battery bank because that's what he wanted. So anyway, residential battery markets are different than commercial. So what we're going to do after the break is we're going to kind of wrap up a couple of economic case studies, and then we're going to review some battery spec sheets and kind of talk about the battery design process. So it's about, let's see, I kind of went on a little long. It's, oh, no. I've been reading my clock wrong. So we're still good to go. We have about 40 minutes before our break, so that's great. Okay, so let's see. Now I gotta switch back over into my updated slides. You can't draw on these as well. All right. Okay, so here we have an off-grid example for limited use structures. And these structures are those that have their own electric service, that are being billed for their own electric service, but they use such little electricity that the cost of the electric service itself is a pretty big fee. So in one of our classes, we start out the class by going through a design exercise where we have a fridge, a ceiling fan, a few light bulbs, and we get their power level and their time level and their watt hours level. So if this is like an off-grid hunting shack and we're looking for a 1,000 watt output from the battery bank, and the solar array needs to generate 8 kilowatt hours a day to fill those batteries back up. But in this case, we are only using the battery bank on the weekends. So we don't need 8 kilowatt hours a day. So anyway, so we don't need an 8 kilowatt array. This is going to be a small solar array, a small inverter. If it's off grid, there's high-end battery inverters that have all of that functionality that we talked about. There's also cheap battery inverters that you would find at like a boat dock or a marina, that they're not very good inverters. They don't have high quality. You might not be able to run a cook stove or some high wattage appliance on that. But they're not listed for grid connection, which means you can't grid connect them, but they make cheap off-grid inverters. In other words, you wouldn't want to have them in a house, powering a house, because they're just not reliable, not functional enough. But for a little hunting cabin, sure, why not? And so we're talking about a 1 kilowatt solar array and a 1 kilowatt inverter. And if you're prudent with that budget, it might be that your total system, if you're getting a few batteries and a couple of solar panels, you might be able to piece together a system that has a 8-year payback. If you're paying a couple $1,000s for your transformer, then you might see a payback that is immediate. Because if there's no electric service already on site, at bare minimum, they have to hang a transformer on the power lines and wire the power out to your property. That's going to cost a couple $1,000s. So the kind of rule that I have is, if you look at your electric usage and you see how much we're using 8 kilowatt hours a day for 8 days a month at 12 cents a kilowatt hour, that comes out to be $8 a month. And the grid access fee in this case is $29 a month. So we're spending more money on our grid access than we are on our electricity itself. These are cases where it's good to consider going off grid today. Otherwise, you have a luxury residential market, and then you have an economic-based commercial market. And most solar installers end up, because it's a luxury market, they know that it's going to be an expensive solution. Most solar installers will tell the customer, use the solar array when the grid is active and use a backup generator when the grid is down. That's the most cost-effective option for your client. Of course, the problem is what happens if you run out of gas. If you're not generating your own power and it's an emergency, you might not be able, you still might run out of power. So on-site power generation does offer some energy security that a gas generator doesn't. And often it might be that you combine the systems and you have a gas generator and a battery bank. In fact, as we'll learn momentarily, flooded lead acid batteries essentially require a gas generator for maintenance. All right, so our client came to us and said, we want to do an off-grid home, and gave us a couple of design options. It's going to be in an air-conditioned environment that's dust-free. So the batteries are going into a garage, but we're building a room in the garage with an air conditioning unit that'll filter the dust out of the air and also ventilate the room. Batteries are required to be vented, and an air-conditioned room qualifies for the vented requirements. But another problem with batteries is that the gas that they emit is corrosive to metal. And so it's best, even if you're in an air-conditioned room, to capture the gas as it comes out of the battery itself and vent it directly to the outside. Now that's for lead acid style or flooded lead acid type batteries. Lithium-ion batteries are still very expensive, but there are batteries that don't emit gas or that capture their gas. They're just not, they're more expensive, and so we're trying to go with the cheapest, best technology just to make the project feasible. We're doing a backup generator, and what that backup generator is doing is that it's protecting the batteries from a deep discharge. So the client actually told us that he did not want a generator, and I responded back saying, well, you need a generator to maintain your battery bank. So one of the maintenance tasks for your battery bank is to overcharge them every so often. And it comes out to be about maybe once every 3 weeks. So you might do it once every 2 weeks or maybe once a week during periods of heavy usage. And then you can take it easy during periods of less heavy usage. But what you're doing is either overcharging the batteries from the grid or overcharging the batteries from the generator. Could you use the solar array to overcharge your batteries? Yes, but then it just might be an unreliable process because clouds could come over the array and trip the system. So generators are good for maintaining battery banks that emit gas, primarily flooded lead acid. But on top of that, the generator is also preventing the batteries from going into a state of deep discharge. So we're going to learn in a little bit that there's a couple of different stages to battery charging and discharging. And it's kind of weird because the battery voltage, the batteries are rated for a higher voltage, but then they have a nominal voltage, which is kind of their operating range. So batteries are rated maybe for 60 volts, but you'll still call it a 48 volt battery bank because that'll be kind of their operating voltage. That maintenance charge will take them all the way up to almost to the top of the 60 voltage range every so often to help maintain the insides of the batteries. So anyway, because we're using a generator, we can get away with a smaller battery bank. But my client said he doesn't want to have to rely on a generator. In other words, if he's running his generator, it's because he's doing the maintenance mode. He doesn't want to have to worry about, in that winter storm, hearing his generator click on and thinking, oh no, I'm going to run out of gas if I don't fill the generator up. So he wants a system that could function without the generator, but then we're still adding a generator onto it just for maintenance and conditioning the batteries. So in other words, we're not reliant on the generator, but we're still using it very much so. What that means is he has to do a larger and larger and larger battery bank, and that's okay. Essentially, if you do a larger battery bank, if you have a battery bank that's twice the size, you're going to cycle it half as much, and you're going to get, almost twice as much life out of the battery. So, overbuying your batteries and having your batteries last a very long time, the main problem is that you're buying so much storage capacity that it's expensive, but it's often, it's often recommended. Let's talk about the tax credit for a minute. The solar tax credit of 30% applies to the batteries. And while I'm not a CPA or an accountant, I've heard from other solar installers. I've never done this myself, but I've heard from other solar installers that when you retrofit a solar array that was originally eligible for the federal tax credit, so one that was built like from late 2008 forward, that if you retrofit a battery bank onto it, that the batteries will qualify for the tax credit even though it's a retrofit project. So anyway, you get a 30% tax credit on your battery bank and those components, and that's supposed to step down after 2019, but it's not stepping down by terribly much. So you have some time to kind of dream about a battery bank and claim that tax credit. The tax credit could always be canceled. I mean, I think that if they do tax reform, that there's no way that the tax credit will stick around. But on the other hand, maybe you'll have more money to do a solar array with. So there are different kinds of battery technologies on the market. The main one that we use today are advanced lead acid. And this is kind of funny because when I called up Energy Toolbase, the software company, I said, what kind of batteries are your customers using? They said primarily lithium ion or other kinds of lithium batteries, which is this larger rectangle. And then I called up Schneider, which is the inverter we're using for our off-grid system, and I said, well, what kind of batteries are your customers using? And they say almost exclusively lead acid. Now, there's this, there's different pockets of the battery market that are serving niche market opportunities. But anyway, what we can see from this graph is the big difference between an advanced lead acid battery and a lithium ion battery is that lithium ion, they say it's more responsive. So anyway, with a lithium ion battery, you can discharge it faster and you can also charge it slower. So it's all around a more elastic battery. And what happens with a lead acid battery is the quicker you discharge it, the less efficient it gets. So it may take 100% of electrons to charge it up to its state of charge. But if you want to discharge it in 2 hours, you might only get 60 electrons out of that. Whereas if you discharge it in 5 hours, you might get 80, and if you discharge it in 20 hours, you might get what it's rated for. So the faster you charge and discharge a lead acid battery, the less efficient it gets. That may or may not be a big deal. And for commercial demand management, you might think, well, I need a battery that's going to last a whole bunch of cycles and fully discharge and fully charge and be very efficient, and I don't have to worry about discharging it and damaging the battery. Then again, lithium ion costs a lot more, so maybe the battery that you use and you wear out and you replace, maybe that's the more economic option. It's kind of interesting to see lead acid and lithium ion kind of duke it out. Now I can tell you where lithium ion is used is utility pilot projects, because they want to see what the future technology looks like, and everyone thinks lithium ion will be the future. Two, lithium ion is used in remote weather monitoring stations and other applications where maintenance functions are difficult or can't otherwise be performed. So you go into your top shelf lithium ion batteries and they'll last for 30 years. They'll last for a long time, but they'll also cost you an arm and a leg. But they fit the purpose because you save on the maintenance costs. So anyway, lithium ion definitely has niche market opportunities. I think that it's the battery technology of choice for commercial demand management, but that's primarily because the location has a storage subsidy, which is California. That means you can buy a more expensive product and still get a payback on it. And then two, your mini facility managers, they don't want to do the maintenance that's required of a flooded lead acid. But that does beg a question that says, well, if you have a warehouse and you're on a demand rate structure and you have a facilities person on staff who can do battery maintenance, maybe you have a fleet of forklifts and you're already doing some battery maintenance. There's really, you should still consider the advantages of the cost advantages of lead acid because they're so much cheaper. In terms of other technologies, flywheels and capacitors are really being used for quick charging and discharging cycles. So like in elevators, where the elevator is going from floor 1 to floor 20 in a couple of seconds, and then from floor 20 to 1 in the opposite amount of time. Those are good opportunities for storing mechanical energy. Other kinds of batteries, flow batteries get a lot of attention because they essentially are batteries that can cycle, if not forever, for a very, very long time. But they're still kind of in experimental phase. In fact, one of the more popular flow batteries, which is an Australian battery company called Redflow, they really never got out of Australia, to my knowledge, but they've recently announced that they're not looking at residential markets. They're looking more at commercial markets or utility scale. So their flow batteries really have not found a strong market position yet. Some of these other batteries are just different materials. Mechanical storage like pumped hydro. Pumped hydro is actually a pretty popular utility scale option. It's basically a dam that you pump water up and use it when you need it. But it's costly, and they're doing rail car storage that does it the same thing but with trains and weights. And all of that is costing so much money in the pilot phase that it really makes me a big fan of chemical storage rather than mechanical storage. So lastly, you take a look at the growth charts in lithium ion, and the whole industry is growing. Lead acid is growing too, but lithium ion's really the one that that's driving the growth sector of the industry. So I don't think anyone out there thinks that 10 years from now, lithium ion won't be the standard option. But if you need to do the solar project today, lead acid is still a contender, provided you're willing to do some battery maintenance. There's a couple of different kinds of batteries on the market. I've categorized them this way, but I've done I probably should add a few more to this list. When we went out to evaluate the off-grid project, we started with flooded lead acid. Then we looked at sealed batteries, which don't require any maintenance. But we didn't really look at those because lithium ion are also sealed and don't require much maintenance. And the thing about AGM versus FLA is the sealed AGM batteries are more expensive than FLA, and they're also not as robust. They don't have as many cycles. They're just not as long-term of batteries. They're really what the option was for people who had giant maintenance costs because of the location of what they were trying to power. So we knew pretty much off the bat that we're either going to go with the cheapest solution, which is a flooded lead acid technology, or we're going to do the lithium ion, which has high upfront cost but a pretty good overall price point. Then you get into top shelf batteries, which are usually lithium ion batteries, but they have additional elements in them. So instead of being lithium ion, it would be called a lithium iron phosphate, which has phosphorus and sulfur and oxygen. And it improves the battery life, but it also makes the battery more expensive. I mean, the thing is, when you buy a 4-year battery, you're buying 4 years worth of use out of it. When you buy a 10-year battery, you're buying 10 years of use out of it, and that might cost you 2.5 times as much. These lithium iron phosphate batteries that last for 30 years, they can cost you, 3 times as much, if not more, than a battery that will only last 10 years, because the buyers of these long-lasting lithium iron phosphate batteries are buyers who really, really don't want to do maintenance ever again at this time because the price is so high. So, if I have unlimitedly deep pockets and I never want to maintain my battery, then I would go top shelf. But that's the only reason. Otherwise, lithium ion or flooded lead acid seem to be the preferences. So actually, we then added another option to our list. We found a nickel iron battery that's very similar to a flooded lead acid battery, and they had a reasonable value proposition, so we evaluated them as well. So we're looking at nickel iron, lithium iron phosphate, lithium ion, which is a cheap lithium ion technology. Tesla makes a cheap lithium ion battery. I'm trying not to say that's not quality or one way or the other. I don't have a Powerwall. I don't have any experience with the Powerwall because they're not very available yet. But their lithium iron phosphate is a higher quality battery than what the lithium ion that Tesla makes. Tesla is really trying to make a cost-effective battery, not necessarily the best battery. And then there's flooded lead acid, which has the least upfront cost and the most market experience. And so, especially with off-grid, you don't really want to mess up. So we looked at a couple different battery technologies. Then we looked at some charge controllers. Here's our options. So these are all the popular high-quality residential charge controllers in the U.S. market. So we had Schneider 600 volts, the Morningstar 600 volts, and then Outback and Midnight/SMA. And the reason is Midnight makes the charge controller, but it's fully compatible, visually compatible with the SMA inverter system. And so this is actually something that surprised me, is that Outback and Midnight/SMA come very highly recommended. You know, SMA is known throughout the entire industry for their quality inverters, and Outback in the off-grid market kind of built a reputation around that too. But the problem with these two charge controllers is they only go up to 150 volts. And so a solar panel is about 40 volts each. And so you got 40 volts there, 40 volts there, and then maybe you can squeeze another panel onto it, or maybe not, you know, depending on your temperature correction. And so we're dealing with these kinds of 150 volt charge controllers. You know, your panels are going to go on 3 module circuits. Now, normally to get up to 600 volts, you're operating at maybe 500 volts normal, and then it gets temperature corrected up to 600. And so we could actually put together, you know, maybe 8 or 9 modules before we get up to our limit. And then even if we go and use a SolarEdge system, which provides some additional optimization, maybe a SolarEdge circuit, you might be going up to 14 modules or so. And now, you know, that's a 14 module, 600 volt circuit before you go to the next circuit. Well, now our circuits are now 3 modules each. And I was thinking to myself, well, it takes so much more time to wire up. If I have, our array is 80 solar modules. So if I have 27 circuits of wiring to do on a rooftop versus 8, you know, that's a huge difference. And this project is actually a do-it-yourselfer scope. So, you know, I wouldn't think that any new to solar installer could really wire that up successfully. Maybe if it's on the ground and you have an elevated rack that you can get underneath, but these 150 volt charge controllers were really designed and developed around a much smaller application. You know, back when solar was expensive and people who did live off grid, you know, really were Spartans with their electric use. What we're trying to do is just take a regular old house off grid. So we wanted to do a 600 volt for certain, and both Schneider and Morningstar had very good reputations, and we just ended up going with Schneider simply because they also do Square D balance of system material, and they had a lot of market experience with this 600 volt charge controller. Morningstar's charge controller is only about a year on the market at 600 volts. So, you know, reliability and product testing kind of won the day on that decision. So we're doing Schneider, and then Schneider has that option where we could put the inverter, we could have the solar array on its own inverter and the battery bank on its own inverter. And so we have that option, or we could use those charge controllers to go into our battery and just have our one inverter group. And so what are we going to use? You know, are we going to use a charge controller or just inverters only? Well, there's actually a term for this. You know, when you go from, when your charge controller and your solar array is landed on the same kind of DC bus, that's called DC coupling. Whereas when your solar battery inverter and your solar inverter are next to each other on the AC bus, that's called AC coupling. So the question becomes, well, which is better? Is DC coupling better or is AC coupling better? And the answer is it depends on your application. So every time this electricity, is processed, that's a step, and that represents efficiency loss. And so for energy to come out of our modules into our battery bank, that's a one-step process. And then go from our batteries into our load, that's a two-step process. And then the same step, if we go from our solar array through our inverter, and then go from our inverter through our battery charger to get it back into DC, and then go from our battery bank into our load, that's a three-step process. And that is less efficient than a two-step process. But here's the thing. If you are grid connected, this two-step process is going from the solar array into the batteries through the inverter, and then the inverter into the grid. Whereas in this case, if we're grid connected, our solar modules just go one step into the load or into the grid. And so the question is AC coupling or DC coupling better? The answer is, there's really two answers. The first answer is, well, it depends on the use. And the second answer is, the costs are so close together that it's really not worth worrying about. Just do what seems the best for you. But if we had to split those hairs, if you have an existing solar array already on site, AC coupling is the logical choice. Just do a battery inverter with its own battery bank. If you are grid connected, do AC coupling, because with AC coupling, that one-step process into the grid means when you're selling back to the utility, you have the least amount of efficiency loss. So when you're selling back to the utility, you do AC coupling. When you are retrofitting an existing solar array, you do AC coupling. Where you do DC coupling is if you're trying to live 100% off grid. And the reason is you only use the batteries, you only use your solar array for a very short period of time, when the sun is up. So your solar array turns on at 8, it turns off around 5, and you're only using the solar array at that time. For most of the day, you're running off your batteries. And so if you're primarily running off of a battery bank, you want the most efficient process to get power out of that battery bank. And that's a two-step process versus a three-step process. If you're selling it back to the grid, the most efficient process is a one-step to sell back to the grid, and your batteries just kind of hang out and are primarily used for backup power. So grid connected, AC coupling, off grid, DC coupling, but AC coupling is okay too. Utilities like AC coupling for their utility scale battery banks. And I think that's because not that DC coupling is worse, but that AC coupling makes more sense for grid connected solar arrays. All right, let's see. So going back through our program, getting us back to where we are. We saw these slides already. All right, so let's talk about some balance of system material trends. Up on your rooftop, to be rapid shutdown compliant, the one issue is we've gone over to microinverters and DC optimizers. So behind every module on your rooftop, there's a little box, and it's for your microinverter or DC optimizer. And then the problem is, now you have all these little boxes on your rooftop, and they fail, and we cover that in other classes. But also, the microinverter storage system in particular with Enphase, and maybe they're just not as elegant, or you don't need them anymore. They're more expensive. But the problem is you may find a string inverter that's a battery inverter, like Schneider's string inverter is not a microinverter system. SMA Sunny Island is not a microinverter system. Outback is not a microinverter system. There are, Magnum, I believe, has a microinverter system now. But all you need is a rapid shutdown compliant combiner box, or maybe a string optimizer rather than a module level optimizer up on the rooftop to go back to your inverter and keep it rapid shutdown compliant. So it's, you know, you can shave a little bit of cost off of your project by moving away from microinverters or module level electronics by incorporating the rapid shutdown compliant combiner boxes. And you might find that that's a good strategy if the client wants a battery inverter, just to go with, if you're buying the whole system at once, what you're going to want to look at is kind of a DC coupled solution, and that way you buy everything integrated and it's the lowest upfront cost. So anyway, the least upfront cost system design for an off-grid system that is code compliant is doing a DC coupled all-in-one battery inverter, but don't forget to maintain rapid shutdown compliance up on the rooftop. And there are some battery inverters on the market for utility scale. ENGIE makes one. And then also, if you're not yet ready for batteries, if the batteries are too expensive, we did this for the owners of Half Moon. They want to go off grid, but they only had a $15,000 budget. And so this was in 2016. We said, well, you only have 15 grand. Let's build the largest solar array we can now, and then later add batteries onto it. So we went with the SMA system. It was a ground mount. We didn't need to have rapid shutdown compliance. But one thing that was interesting about the SMA system is they actually have a separately derived power outlet that's hardwired to the inverter. So you could wire that up. That could be an internal outlet. We just put it on the outside of the home. And that'll allow you to have a source of power during the day during a power outage without batteries, which is, some installers think it's a gimmick. I think it'll do in a pinch. You know, having some power is better than having no power. But it's not a true off-grid system. We're going to take a break in about 2 minutes or so. So right before the break, let's talk about how batteries work. This is coming from a lecture by Professor Jeff Dawn. He's a Canadian professor, and he's a battery professor. And he started posting his lectures online. And then pretty soon after he posted this lecture online, he got a job offer from Tesla. And he doesn't post his lectures online anymore. That might tell you something about the value of his lectures. But this battery lecture is really good online, and there's a transcription too if you'd rather just read through it on this link. So he said a few things about batteries. He does battery experiments, primarily trying to improve the cycle testing process of batteries. How a battery works is that you have this electrolyte that can transfer positively charged ions from a anode to a cathode. And at the same time, you'll have an electron coming out of the anode and flowing into the cathode, and that'll drive the load. So it's this ion exchange that provides the motive force for the electron to come out of the anode and flow into the cathode. So, you know, as this cathode is getting positively more positive ions, it's also going to want to suck up more electrons in short. What's interesting is what fails about a battery is not the cathode or the anode or the electrolyte itself. The cathode only degrades by 3% mass and the anode by 10%. So there is more degradation in the anode of a battery than there is in the cathode. But what happens is it's the barrier between the anode and the electrolyte becomes plated. So as the ion gets passed through the anode, it leaves behind a solid that slowly plates the anode. And some of the battery research is, well, how does this have to be a solid? Can it be a gas? Can it be a liquid and just go into the electrolyte? Can we change our electrolyte slightly so that this process produces less particulate and less plating? And that alone can take a battery life from a few years into the 10-year range, is just by testing the electrolyte. But that he ran into a different problem, which is if you're designing a 10-year battery or a 30-year battery, how exactly do you test that, given that you want to test it in a matter of weeks rather than a matter of decades? And so at that point, he began making his own test equipment that gave a higher resolution of imaging, and that was really what Tesla was most interested in. Now, batteries have a charging efficiency and a discharging efficiency. For the purposes of solar design, I don't worry about the charge and discharge efficiency as much as others. The reason is you're not running off the batteries primarily if you're grid connected. If you are running off the batteries while you're grid connected, it's because you have that, it's economically beneficial to do so. And so when you're running a commercial battery bank for load shaving, you might be saving $5 an hour, and it really doesn't matter if your electricity for that hour cost you 15 cents or 30 cents. It doesn't matter the efficiency loss of that. You're saving so much more than what the cost of electricity is that it doesn't matter. Likewise, when you are running off the batteries in an off-grid setting, that's not desirable, and the charge efficiency has something to do with that. But you kill the charging efficiency issue by just overkilling it with the solar array. So with an off-grid solar array, you're often designing a solar array that might be 60 to 100% larger than for a grid-connected solar array. So if your solar array is usually overly productive and only underproductive on overcast days, but even then it's sized large enough so you get some input out of it, the charge and discharge efficiency ratio doesn't play as large of a role in the design process as you might think. And of course, less efficient batteries tend to cost less too. Looking at temperature requirements for batteries. So we're using a lead acid battery, and that lead acid battery is rated for 120 degrees Fahrenheit. However, it says if it operates at 100 degrees Fahrenheit, that it can damage the battery in the long run, and its suggested maximum operating temperature is about 90 degrees Fahrenheit. Now, what's going on with batteries and temperature and cycling? What we see in this graph on the right is number of cycles and the percent capacity remaining at elevated temperatures. And even with lithium-ion batteries, so this is not just a lead-acid issue, but even with lithium-ion batteries, the higher the temperature goes, the less, the higher the degradation occurs. So you don't want your batteries to be hot. Obviously batteries are hot. We have lead acid in our vehicles, and underneath your car hood in the summer, your batteries can take the heat, but it's still not good for them. So that car battery, you need to do it. You buy a $100 battery, and when it conks out, it conks out. We're talking about buying $30,000 or more worth of batteries. We're going to take care of them. Then we get into another chart, and we're going to look at this chart in greater detail after the break. But this is called a depth of discharge chart, where this curve here is the depth of discharge starting with, this is about a 20% capacity, and this is fully drained. And this is how many cycles you can take. So we're going to come back to this chart in greater detail after the break. Let's finish off our temperature discussion here. This is our capacity of our battery at various temperatures. And what we can see is actually as the battery gets hotter, its capacity increases. It's just not good for the battery. As the battery gets colder, it starts to decrease, and the issue is the batteries, if you can see here, this is 0 degrees Fahrenheit, and batteries can actually go into below freezing temperature ranges, but they have to be charged up. You can't, if this battery is only 20% full, it might freeze. And so that would be another reason to have a generator in the wintertime is to make sure your batteries don't freeze on you. But anyway, what he determined was that that temperature is the enemy of battery performance. It's best to keep your batteries from overheating. If what I'm trying to say is you don't need to put lead acid batteries in a conditioned space, but if you can, it's a good idea too. Okay, so finally, and let's finish this. I'm a little over our break time. We'll take a break at 1/4 till. But finally, we get into our design process, and we're trying to determine how large of a battery bank that we actually need. And one problem with this home is that it's a new construction home. So the client has given me how many kilowatt hours a month his home uses. And what we can see in this graph is we have higher usage in the winter time than we do in the spring and fall. But then in the summertime, our usage goes up to our maximum. And so what I would do in this design process is I'd take the monthly total and calculate a daily average production. And then, or a daily average consumption. So we've taken how much energy is consumed, come up with how many kilowatt hours a day we need to come up with and for the month. And then I would go into PV watts and I would say, okay, well, what's the largest solar array I need so that in the month of January, I'll average 48 kilowatt hours a day. For the month of February, that I'll average 56 kilowatt hours a day. And what we can see is if I do that for the whole year, like you would for a net metered solar array. So this home uses, let me make this a little bit bigger. So this home uses 1,700 kilowatt hours of electricity a year. And if I net metered this solar array, what I would do is I'd go into PV watts. You've probably seen this in other classes. I go into PV watts and I put in my location. In this case, it's Starkville, Mississippi. And this will be on a rooftop, and it's about a 412 roof pitch. And I'm being conservative in my estimate, I'm just keeping everything the same. I'm going to go and model a 1 kilowatt array. And I go in and put it on the rooftop and give it my 412 roof pitch, and it's south facing, so we click go. And so in Starkville, Mississippi, 1 watt of solar produces 1.368 kilowatt hours of electricity. And so let's go ahead and look at our client's electric bill. Let's see, where did it? Our client is using 17,100 kilowatt hours of electricity a year. So if we did 17,100 divided by 1.368, our client would only need a 12.5 kilowatt solar array to net meter this home. So this is a typical, on the smaller side, energy efficient home in the South that's for a family of 4. Uses a lot of electricity, suburbanite style home. But the problem is, if we did a 12.5 kilowatt array, we would have all the power we needed in March, and all the power we needed in April, and all the power we needed in May. But June would cut it close, and then we would need more power in July and more power in August, and then we'd be okay in September, October, November, but we need more power in December, and we need more power in January. And then again, remember, these numbers are all based on daily averages, but we actually have more variability than that. We could have an overcast day or a storm cycle that would drain the batteries, and the batteries would need a few days to make it all the way back up to a full state of charge. So, if we don't want a generator in this design, then we need a solar array that is at least 18 kilowatts in size, if not larger, because we're erring in this estimate by not being conservative enough with our sizing. And so, what I concluded was, well, we need at least an array that's larger than 18 kilowatts. And I like buying by the pallet. So at that point, it's saying, well, how many watts come in a pallet? So do I need 1 or 2 or 3 or 4 pallets of modules for this solar array? So anyway, we could get away with a smaller solar array like a 12 kilowatt if we had a generator on site, which we do. So we don't need to do such a large solar array. But one, we're already on site. Solar panels are relatively cheap, and so we're just going to overkill it on the solar panels and install more solar than we have to. No big deal. 2, the client told us he doesn't want to have to worry about his generator, and so we're trying to do the system such that if he never used his generator, he still would not run out of power. So it's a security issue for him. He wants to make sure that he can build his off-grid array, but he doesn't want to lose electricity and fear the repercussions from his family for building an off-grid house and now they don't have electricity. I don't want him to have that situation either. So in our battery sizing, what we need to do is, we know we have a 19 kilowatt solar array or around that size. We have these monthly totals and these daily averages. What we want to do is build a model that will show us for our array size, how large of a battery bank do we need, and then what we're modeling in the right-hand column is for that month. We know how much power we're producing from PV watts. We know how much energy we're consuming from PV watts. If we divide that by our total battery capacity, we will get an average depth of discharge for every day and every month. And what we can see is that for this 110 kilowatt hour battery bank, the average daily depth of discharge is 28%, but in high demand months, in July it goes up to 40 or 45%, and then in lower demand months in March and April it's only like 18%. So our average depth of discharge, there's more to the story. When you go and you look at your depth of discharge charts, let me see if I can make this one a little bit bigger. So here's our depth of discharge chart. What you would do is you'd go and look at how much you're normally cycling at. And so, we were at, for the year, we were at an average daily depth of discharge of 28%. So we go down to this chart and say, okay, if my 110 kilowatt hour battery bank is going down to 28%, what that means, here's 28%, what that means is that I'm going to get, it's a little bit lower than that, I'm going to get about halfway in between here, I'm going to get about 2,750 cycles out of my 110 kilowatt hour battery bank, of which only 30% of it is being used on a regular basis. So I know I'm using 30% of the battery 2,750 times. And so if I have my battery cost, how much energy came out of it, I can do a cost of storage calculation. So what we're going to do is we're going to take a 15-minute break. We're going to pick back up at the top of the hour, and we're going to walk through some cost of storage calculations for you. So it's not that you can't go anywhere. Feel free to stretch your legs. We'll see you back here in 15 minutes at the top of the hour. We're going to get started again in about 2 minutes, so right at the top of the hour. All right, getting back into it. All right, welcome back. We were talking about battery sizing, and we're starting to get into this chart that I would call a depth of discharge chart. And what I want to do is just spend a small amount of time walking you through that process of how to start modeling, like how do you know what your depth of discharge is going to be, and maybe some of those commercial softwares like Energy Toolbase or maybe System Advisor Model. You play around with it, you can figure it out, but I want to show you a simple way to do it. Kind of the pencil and paper method, if you will, but you're going to have to use Microsoft Excel. But here we are in PV watts. So in other classes, we cover our PV watts calculation. And this is for a 1 kilowatt array, just as an example. Why don't I go back and do something a little bit more realistically sized. I'll go and do a 10 kilowatt array. And this will just be, as you can see, it's just all the numbers multiplied by 10. No big surprise there. But anyway, I'm a big fan of this download monthly or hourly results, and I'm going to download the hourly results. And what we get is a map. Here's our PV watts data, and it's an hour by hour printout of what the array will produce. So here on January 1st at high noon, our 10 kilowatt array is around 2.4 kilowatts, and it must be a cloudy day. And well, look, for beam irradiance, we have two columns in PV watts. We got beam irradiance and diffuse irradiance. And look, on January 1st, we don't have any beam irradiance. We only have diffuse irradiance. And the next day, same thing. It's mainly diffuse, a little bit of direct. See how it kind of has a peak here? And then the next day, we have a lot of beam irradiance and not much diffuse irradiance. And what this is it's the weather data that is collected from the PV watts weather station that we specified, right on this page right here, where, let's, yes, we change our location. Anyway, these are all the PV Watts, weather stations. They're all over the place. So, this is actual recorded weather data. And what's important about this data is that it models things like, well, how many days in a row is my overcast weather system in the month of December? So you can estimate the weather patterns, and that will translate into a total system output wattage. And so if you know how many kilowatt hours you're going to produce, if you know your production, and then your consumption, all we know right now is our monthly consumption, which we put into, all we know right now is our monthly consumption, which we put into our daily consumption here. And so what we would then do is put in our hourly consumption and the starting, and whatever this is, if it's in the month of winter, here's 48 daily kilowatt hours consumed. So what I did at this point was I was really conservative. I said, okay, we're doing 48 kilowatt hours consumed in the month of December. So that's going to average to 2 kilowatt hours a day. And this is actually in kilowatt hours, and or an hour. And so that's actually going to model more drainage of the battery bank at night, which is conservative, because I'm going to have more power consumption during the day and less in the middle of the night. But what we do is we subtract our kilowattage of column K, our system output. We have our consumption minus our system output, making sure they're all in the same units. Uh-oh. So we need a total column, and we subtract the two, adjusting for our units, and that gives us the kilowatt hour difference. So now we are, and actually that's all, since we're losing, we multiply all this by -1. And so in that hour, we've lost 2 kilowatt hours out of the battery bank. In the next hour, 2 kilowatt hours. The next hour, 2 kilowatt hours. And so basically what you can do is you can track the power level on an hourly basis in Excel and see, well, how does the battery bank interact with the consumption of an average day, but when the weather conditions are overcast, or if you have a multi-day storm cycle. What we're going to do is we're going to chart that out and visually inspect it. And that's going to help us determine how large of a battery bank that we need. But anyway, at the end of this exercise, we get to 28% depth of discharge with a 110 kilowatt hour flood acid battery bank. And at that point, we need to go and look at the life cycle chart. And so we start doing our battery research, and this is a Trojan battery that's a 4 volt, and here's a different 4 volt. This one's 1200 amp hours. This top one's probably stronger than that. Let's take a look at some of these spec sheets here. So Trojan battery product line. We actually didn't look at we didn't go with a Trojan battery. We went with a different battery. So that's all right. What I'm trying to look is they usually have a catalog. This might be it. So we're going to look at a few batteries. This is a industrial battery. It's kind of a top of the line. It has a 1600 amp hour rating. It would be pretty pretty expensive. This is 4 volts at 1600 amp hours, and the dimensions are 27 inches long and 23 inches tall. These are pretty big and pretty heavy batteries. Then we go to this one, and it's the same voltage, similar dimensions, a little bit smaller amp hours. Anyway, this is one of the batteries we evaluated, and then what we see here is this charge depth of discharge sheet. And so hopefully this is a little bit more clear. So now we're at our 28% depth of discharge that we calculated from PV Watts and our consumption estimates in Excel. And that's coming out to being about 4,200 cycles. Now this is what I want to show you. We're going to go into a different Trojan battery. So same company, different battery. This is not in their industrial line. This is what they call their premium battery. And this is different than their signature battery. And they'll tell you that all of them are for renewable energy applications. And so what we want here is the specification sheet. So here's the spec sheet for this battery. It's the same flooded lead acid battery. Its voltage and amperage is a little bit different. This isn't a 4-volt battery. This is a 6-volt battery, and the amp hours are much smaller as well. And if we go and we look at this battery, I want you to look at 2 things. One is, if we did 110 kilowatt hours, the same size battery bank, and we got down to a 28% depth of discharge, and we go up here, the cycle rating for this is only 2,750, whereas with the lead acid battery we were more up in the 4,200 range. And so there is a huge quality improvement in cycle life between going from their signature product line to their industrial product line. Whatever those terms mean, there is a top shelf lead acid battery and a mid-range lead acid battery. And in terms of product life, 4,200 cycles instead of 2,750 cycles, we're getting 50% more product life out of the top shelf lead acid battery than we are off of the mid-range lead acid battery. Well, guess what? The mid-range lead acid battery is cheaper by about, the reciprocal. So So it's by going with the industrial battery, it really what you're doing is just getting larger capacity, maybe a tiny bit of an increment in economies of scale. But essentially lead acid is lead acid. Now that does beg the question, if there's a top shelf and a mid-range, is there a bottom shelf? And yeah, you can go and find other 12-volt Trojan batteries, and there's a big price range difference too. So coming back into the lecture, we go through this exercise for a couple of different battery banks. One was 110 kilowatt flooded lead acid using the signature batteries. The how many cycles was it? It was 2,750. Yeah, that's what it was. Divided by 365 days a year, that's going to last us about 7.5 years or so before it reaches the end of its useful life. And then at 110 kilowatt hours, if he's using 48 kilowatt hours a day, he could go 2 cloudy days without running his generator, or he could also realize it's cloudy outside and curtail his power too. Here's the thing. this 7.5-year battery is $120 a kilowatt hour, and it's rated for so many cycles. So to get its total cost, there's an upfront cost, but then there's also a total cost of storage usage, which is the energy out over the life of the system divided by its cost. We also compared this to a 67.5 kilowatt hour Tesla Powerwall 2. And the 67.5 Tesla Powerwall 2 actually lasts for 16.6 years. So we get a much longer life out of the system. The problem is the upfront cost. $22,500 is really not that bad compared to $13,000. The problem is the storage capacity, because this battery, even though it might be cost effective, it only gets me through 1 day of winter, whereas the lead acid gets me through 2 days of winter. And so the question is it better to have the capacity for the winter time when you really need it, or is it better to have a slightly more cost-effective battery that drains your budget so you don't have the storage capacity that you actually need? And that's kind of the trade-off you're being forced to make right now. And it depends on your design again. If you're grid connected, you don't need a large battery. You're only using it for blackout circumstances. So you just need a small lithium-ion battery, no problem. If you're trying to design an off-grid compound, you're probably just going to go with flooded lead acid anyway, simply because of cost issues. So then we get into lithium iron phosphate, which is the top shelf battery, and we do a 42 kilowatt hour lithium ion bank, and that is not enough to go an entire day without power. That'll get us through the springtime, that'll get us through the fall. On some summer days and some winter days, it may be just enough power to get us through the night, but it's, on your days of high load, you're going to be running the generator as well as using this battery. And this battery has an incredible 30-year product life, discharging it down to 74%. And so a very common sales tactic when you're talking with battery sales guys is they'll say, oh, you can use the top shelf batteries because you can get a much smaller battery. So you're spending more money, but it's on a smaller battery, so your overall budget, there's cost savings there. Well, actually, that's not true. This 110 kilowatt hour flooded lead acid bank cost me $13,000, whereas this 42 kilowatt hour cost me 60 grand. There's a huge upfront cost that you have to overcome the higher quality your batteries get. Okay, so in addition to upfront cost, we want to know what the total cost is, where we have the total cost of the battery divided by the energy output. And so let's go back and look at our examples. The Tesla Powerwall costs about $6 grand for 13.5 kilowatt hours of batteries, and it's warranted for 2,800 cycles. So and it comes with some part savings in it. It has a inverter built into it. So it costs about 12 cents a kilowatt hour if you divide the 6 grand by 2,800 cycles. Flooded lead acid, that signature line that we came out to, costs about 16 cents a kilowatt hour, and the lithium ion, like other kinds of lithium ions, come out to be about 16 cents, like the lithium iron phosphate. And so actually, the lithium iron phosphate solution may be more expensive with a levelized cost of energy than the Tesla Powerwall. It's really that you don't have to replace it. So the lithium iron phosphate batteries are very popular as batteries that you don't have to replace. If I'm sending a satellite up into outer space, that's the battery technology I would choose. But it's not necessarily the most pragmatic one for economic reasons. And then what we also see is, and this point is very interesting to me, is that the lead acid batteries over the lifetime of the product cost more money than the lithium ion batteries over the life of the product. So there's no bones about it. The Tesla Powerwall is more cost effective than flooded lead acid at its current price point, assuming that you can buy one. But one thing that's interesting is the flooded lead acid batteries, they're rated for fewer cycles. And so you don't spend as much money. So coming back to our original example, buying the 110 kilowatt hours for 13 grand versus 67 kilowatt hours for 22,500. And so it even though the lithium ion technology over its life is more cost effective, the flooded lead acid has much lower upfront capital cost. And you got to ask yourself, if you are trying to live off grid, it's a major investment. And with the battery production going into an exponential growth mode, and the tax credit still being around, you may want to do just what's called a starter battery, which is pretty much you go and find the cheapest, $90 a kilowatt hour lead acid battery you can find. These like the top of the line industrial, 4,200 cycles at 30% depth of discharge, they cost, let's look at this list price here. It's $182. So here's our calculator. Here's $182 divided by 6 volts divided by 225 amps. That's $135 a kilowatt hour for the premium line. If we go into the Trojan, why am I on Bing? This is a new laptop. I need my shopping results. Here's the Trojan battery, and it's 4 volts, and its 20-hour amperage discharge is 1,270 amps. And so we take, $1,261, and we divide by 1,270 amp hours and 4 volts. What this comes out to is, instead of being $135 a kilowatt hour, it's $248 a kilowatt hour. And so this battery that costs substantially, that lasts substantially longer, also costs substantially more. So anyway, and it goes in the opposite direction is really what I'm trying to say. So anyway, the concept of a starter battery is, hey, if flooded lead acid batteries range from $90 up to, when you go out and bid them out, maybe $220 in the flooded lead acid range. And then you go and you look at the spec sheet. I guess we didn't reveal this. Got ahead of myself. Here's the cycle and depth of discharge chart for the lead acid battery. And here's the cycle and discharge chart for the let me actually put these right next to each other. All right, so we see the two charts. Probably should have a slide that covers this. But now they're roughly the same. And what I wanted to point out in these two charts was the inflection point on the chart, where the inflection point of this indium battery is right around the 80% depth of discharge. So this battery has been discharged down to 80% before it begins to inflect like that. Whereas this battery's inflection point is right around the 40% range. There's actually a couple of phases in batteries, which they call the, if you notice this starts at 20%, there really should be another axis on this chart that goes down to 0%. It's just that in this kind of range from 100% full discharge down to 80% full, that range it's very energy inefficient to charge from 80 to 100. So that's called the float range, F-L-O-A-T. And that's the range when you're maintaining your lead acid batteries, that you use your generator, your grid connection to overcharge the batteries, and that helps maintain their cathode and anode. It helps bust up the plating that's occurred on the cathode and anode. So your solar array won't charge in that float phase. That's really more for maintenance. So then we have what's called the absorb phase, and then the bulk phase. So this is the absorb phase, and this is the bulk phase. And the essential short of it is you want to stay out of the bulk range. You don't, when you get down into bulk range, you want to turn that generator on and push yourself all the way back up to the top. You know, you don't want to operate in the bulk range. Once you pass that inflection point, at that point, when you operate your battery in this range, it begins to take on more damage. And so the short of it is, this signature line battery really can only operate at a 40% or 35% depth of discharge. And the concern is, in the summertime at 110 kilowatt hours, we're actually going into a 46% depth of discharge, and that's pushing the limit of our battery design. Whereas if we go for the indium battery, we can go all the way down to about 80% before we substantially damage our battery. That $250 a kilowatt hour premium lead acid battery is more like a lithium ion battery that you need to maintain in terms of how deep you can cycle it. So there are deep cycle lead acid batteries, and there are lead acid batteries that you really shouldn't deep cycle at all, and there's kind of a linear price difference between the two. Anyway, the result of this analysis is that the Tesla Powerwall actually looked like a pretty good deal. He has a smaller battery bank. He might have to run the generator a little bit more, but over the life of the Powerwall, it's a lower cost battery. He's looking for a battery that's going to last around 10 years, and that's around or 10 to 15 years, and that's around what the Powerwall would do. So it looks like a great choice. The problem is it's just not commercially available. It's very difficult to find a distributor who can sell you a Powerwall and have it delivered to your house in under, a 2-year wait list or whatever it is. So they really need to ramp up their production. Some of the other lithium ion phosphate companies are in the market today. One of the only reasons why we don't see more of your global battery manufacturers like LG Chem and BYD and Mercedes coming to the market, and they're beginning to, but the price of electricity is so cheap in the United States compared to other countries that batteries get bought before they, all the battery capacity is there's no shortage of demand. So anyway, Tesla Powerwall would have been a great choice, but it's kind of like buying a unicorn. Could be a great deal, but it just doesn't exist. So then we get into lead acid batteries. While researching different lead acid batteries, different product lines, I noticed something about kind of Trojan's product line, is that you can get a 2-volt battery, a 6-volt battery, a 12-volt battery, and the 2-volt battery, the maximum amperage was 1,000. For the 6-volt, the maximum amperage was 370. For 12-volt, it was 200. And they all came out to be around the same energy density. So the question is, how do you decide if you need a 12-volt battery or if you need a 2-volt battery? Well, the inverters, the battery inverters, are often wired to either work with the exact lithium-ion battery you need at whatever its voltage is, or 48 volts. And so our maximum voltage on our batteries is 48 volts. And then we know from our modeling, from our Excel modeling, that we need a battery bank of about 110 kilowatt hours in order for our depth of discharge to be on track. And so, and then the last thing is battery design. And this is where the dust is not settled yet. I've talked to many battery experts who say, here is your inverter on the side of the wall. There's really not supposed to be more than 5 feet between where these batteries are and where the battery inverter is. So you really need to locate the battery inverter right next to the battery. That's a little bit different for solar, where you're just running the battery inverter anywhere. So it's not set in stone, but evidently when you take current out of a battery, even the short distance difference between this bottom set of leads and the top set of leads that are right next to each other, but you can see how just physically this one has to be a little bit longer to make it to the terminal. The pros will take the extra time to make sure that these cable links are exactly the same so that they get the same amount of resistance coming out of them. Because any dissimilarity in these two circuits is going to slowly but surely degrade one group of batteries before the other. And then once one battery starts to fail, very shortly after, more will fail, and then replacement becomes, if only one battery or two batteries fail on you, you can replace them with a brand new battery and just have them be the strongest on the circuit. But once one battery fails, a whole bunch of other batteries are going to start to fail, and so you try and keep the battery circuit outputs the same length to keep the resistance the same. But what that also does is it kind of sets an upper limit for how many parallel strings of batteries you can have. Because if I had 4 strings, then all of these strings would be at dissimilar lengths. The short of it is, I talked to a couple of battery experts, and the consensus was to have no more than 2 circuits of batteries on one inverter. And then I went and I called Schneider, and Schneider said, well, we say you can have 3 circuits of batteries, but yes, you want to make sure that the circuit links are all the same, and then 2 is better than 3. So anyway, what that means is we're limited to best practice. I don't know if I'd go so far as to say it's a best practice, but we're limited to 2 or 3 circuits. And since the batteries are such a big investment, I'm really trying to go for 2 circuits and minimize errors. So we're looking for 2 circuits, but we need a battery bank that is at least 110 kilowatt hours of capacity. And that becomes problematic because, these are all the same. But if I put it on a 12 volt and then I go up to 48 volts, I can only have, 4 batteries on this string. And then there's 2 strings, so that gives me a 16 kilowatt hour battery bank. And that's not big enough. So instead of going with a 12 volt, I could go with a 6 volt. And what that will give me is 6, 12, 18, 24, 30, 36, and then 30, 48. So now I have, instead of 4 batteries on a circuit, I have 8 batteries on a circuit, and I have 2 of them. So now I have 16 batteries at 2.2 kilowatt hours instead of 2.4 versus 8 at 2.4. So essentially what I've done is I've decreased my voltage by half and doubled the number of batteries, and hence I've doubled the size of my battery bank. Well, that's still not big enough. 16 times 2 times 2, that's 24 kilowatt hours. I need 110. So I go all the way down to Trojan's lowest voltage battery product, and that's 2 volts at 110 amp hours. And this is, if I use that circuit, this is what it would literally look like, is we would have 2 volts each going up to 48 volts. And so that is just a heck of a lot of wiring to get to my 48 volt circuit at the end. But that's what, and we're still not quite where we need to be, but that's it. I'm out of product line. So that's kind of what we went out to bid with. And so we looked at Trojan's product line in greater detail, crunched the numbers in greater detail, and yes, there was within the product line, it turns out their most popular battery is also their most cost-effective battery, and that one came out to be 16.5 cents a kilowatt hour, whereas all the others were closer to 20 cents a kilowatt hour. So that was what we were looking at buying, is this 4-volt industrial line for about $31,000. Turns out one of our suppliers recommended that instead we go for a Hawker battery. That's a huge battery. They don't really put their spec sheet online, but it's the batteries are there's 8 of them, and they are 500 pounds a piece. They come on 2 pallets, and so it's like I had to make sure the batteries are showing up tomorrow actually, and I had to scramble a bit because they showed up early, and make sure that we had everything we needed on site to be able to offload something that heavy. But anyway, going through our battery exercise, we designed the system using the Trojan 105 kilowatt hour in mind, or whatever the final size ended up. The next part of the design phase was what I would call modeling the generator usage. And so what this is, it's a graph of the size of the battery bank, and then our PV watts production is every time the graph raises. So here in March, it's like sunny weather, very good production, and very low energy usage each day. So as soon as the solar array turns on, it just slams the power all the way up to the top of the battery capacity, and then slowly trickles at night. So March is no problem. What's taking it down is the modeled site consumption. So this is our PV watts data, and this is our customer consumption data. And what we've done is, here's our 120 kilowatt hour battery bank. And as soon as it drops down to, below 60, so this was modeling it at without a generator. And we get all the way down to, this is 20, so we get all the way down to about 30 kilowatt hours. And what's happening is, here's January, and here's a storm system coming in. And so we go a few days. We go, 1, and then it hops up a little, 2, 3, 4, and then it hops up a little. It hops up a little bit more, but it doesn't make it all the way to the top before it goes back down again, and then it hops back up and hops back up. And we go through like a week and a half long period where some bad weather comes through, and there might be a little bit of good weather in between. But the problem is now we're operating down in that damaging phase of the battery during all this time. So normally we would click a generator on at that point and drive the production all the way back up. Or if you're particularly concerned about always having power, you might even run the generator daily to get top back up. Again, we went with a very oversized battery bank to avoid running the generator. But even with this oversized battery bank, there's still storm cycles in February that will take you all the way down to zero, because let's just face it, there are days that are cloudy, and those cloudy days are often in a row. And so if you just have solar power on site and the sun's not out, you might be able to go a day, but being able to go 5, 6, 7 days, I mean, you need a battery bank that's 5, 6, 7 times as large. Using a generator is probably the most environmentally friendly option. And there's biofuel projects you can do if you really are too concerned about that. So anyway, we modeled what the battery bank voltage would look like without a generator, and then we modeled it with a generator. And so we say, okay, now we model the generator, turning it on so it never discharges below 50%. And it might be that sometimes when we turn the generator on, we coincide it with the maintenance cycle so that the generator overcharges. But we'll cross that bridge when it comes. So what we modeled then is that the generator would need to run a few times a year for mandatory maintenance, and then a few times a year during bad weather to recharge the batteries. So no big deal there. Another battery technology that joined the bid list kind of late was a nickel iron battery. And it was very similar to a lead acid battery, except that the nickel iron battery could discharge all the way down to 80% on a regular basis without damaging the battery. Very similar to a lithium ion, where you can use essentially the full capacity of the battery without worrying about damage. And the thing is, the client had given us this direction to avoid using the generator usage. But we already knew that we would still be running the generator about 20 times a year, even though those would be more a matter of maintenance rather than a matter of running out of electricity. And so the nickel iron battery has more upfront costs. So the question was, well, how small can we get one of these true deep cycle batteries, one of these deep cycle batteries that you're deep discharging every single day? How small can we get it so that the user experience is similar to what the client currently has with lead acid? So he's running the generator the same number of times and it's not running out of power, so it's still a well-sized battery bank where he's not running out of power and only running the generator a few times a year. And so we adjusted our model and ran through a couple of different case scenarios. This is running the generator with good battery maintenance. And then we get into the nickel iron battery. And what you can see is this, you can't make out the units, but this is 120 kilowatt hours down to zero. If you notice, the March and April springtime period is a small level of discharge. Well, now, instead of going with 122 kilowatt hour battery bank, now we're going with a 77 kilowatt hour battery bank. And so we're going not from 122 to 0, but we're going from 77 to 0 with our smaller bank. And you can see how in March and April, we're still kind of up at the top of the battery, although it is discharging a little bit more as a percentage, relative percentage. And we see that the winter time is a little bit more dicey, where, you know, if that generator doesn't click on at this point, if something goes wrong with the generator, then he's going to lose a lot of power. Now, is that the end of the world? Well, not really, because during this wintertime months, you know, the client knows that wintertime months are difficult on his batteries. And so he might be more conscious of, you know, hey, if my batteries are discharging, I need to be more energy efficient. Whereas most of the year, he can kind of relax and not worry about energy efficiency. So it's just the wintertime that's a little bit problematic. As long as he maintains his generator in good working order, you know, he could probably get away with a 77 kilowatt true deep cycle battery compared to 122 for lead acid. So this got into our final cost analysis, where we had a 122 kilowatt hour Trojan 4-volt indium industrial battery bank that would cost about $25,500 with an average depth of discharge of about 30%, cycles up to 4,100 cycles. We saw that on the sheet earlier. That gave us about 11 years at 16.5 cents a kilowatt hour, versus nickel iron, which would cost $52,000 but last 30 years and deliver a price of about 9 cents a kilowatt hour. Now, this was where the things got interesting, because on paper, you know, the nickel iron battery looks like the better deal. There is the upfront cost issue of 50 grand versus 25 grand, but let's face it, if you're taking a whole house off grid, it's a big project. So they might want the cheapest total life cycle. But the client chose to go with the lead acid. And there's a couple of reasons for that. One, we got a competitive bid from a different company that had slightly better pricing and slightly better value. So it was about $3,000 less, and the battery could go up to like 4,800 cycles. So it was actually a better deal that brought the price of this down a bit. But the client, he didn't want a battery, he didn't want a starter battery. He didn't want a battery that he'd have to worry about while his kid is still in school, and he doesn't want to, he has a job, his wife has a job, so they don't have time to mess around with a starter battery like a hobbyist might. But he also didn't want to buy a 30-year battery because battery technology keeps improving. So he kind of split the middle with an 11-year flooded lead acid battery. Says, I get what you're saying about a starter battery where we do a 35 kilowatt hour, $90 a kilowatt hour, a $3,000 lead acid battery bank, and we drive it into the ground and get a good idea of when we're using the battery, why, and how much. And then we go buy the expensive battery that's right-sized. He says, I get that concept. I just don't want to mess with it. Just give me a system I don't have to worry about. I know it's going to cost more, but whatever. He wants to live off grid. He doesn't want to have to live in stress. So he goes with this 11-year, 16.5 cent kilowatt hour option, where even though this 30-year battery option is over the long run, it's more cost effective. And it just serves as a good reminder that right now it's not so much about what is the lowest life cycle cost out of each battery. It's still very important to the client for upfront cost considerations. So anyway, looking at some technical specs for the Tesla Powerwall, you know, there's a couple of things that are interesting. It's rated by kilowatt hour. It's a 6.4 kilowatt hour inverter, but it's also rated by kilowatt, which is output, which is 3.3 kilowatts. And what that means is that the Tesla Powerwall can only deliver 3.3 kilowatts of power for 2 hours, which means that if your home is drawing 3.3 kilowatt hours of power on average, and I'd say most homes do that, if not a little bit more, at least most solar customer homes. You know, what that means is the Tesla Powerwall really only gets you through a 2-hour blackout. It's not a whole house kind of solution. You know, it only delivers 10 amps of power. And, you know, the branch circuit, one branch circuit on your service panel is essentially that. So the Tesla Powerwall costs about $470 per kilowatt hour. And if it's 6.4 kilowatt hours, you know, you're looking at $3,000 to store about 12, you know, if you're paying 12 cents a kilowatt hour for your electricity, it's like for every dollar you spend on your electricity, you're spending $4,000 to store it. So to store a dime's worth of electricity, it costs about $4,000, or it costs $470. So it's not like we're ever going to store a month's worth of electricity. It's just, you know, if you have a $100 a month electric bill, you'd be, you know, spending $400,000 a month. You'd be looking at a $400,000 battery project. So we're not going to buy batteries to store a month's worth of energy. Only if you're going off grid are you going to maybe look at storing a day and a half or 2 days worth of energy, and the generator takes over from there. Or, you know, maybe you go just with a 2-hour generator, and it's not so much that you're trying to have power throughout the entire night. It's really that you want to enable the functionality of your solar array so that you can use it during the day and have a little bit of additional power at night rather than have a complete outage. So anyway, this is what I think is interesting, is if it's $470 a kilowatt hour, you know, the payback at 12 is a very long time out at residential pricing structures. But at the commercial level, instead of evaluating the battery by the kilowatt hour, let's evaluate it by the kilowatt. And so at $3,000 divided by 3.3 kilowatts, the hard cost of the Tesla Powerwall is $910 per kilowatt. And out in Mississippi, we have pretty high commercial demand charges. Out of most of the country is around 10 cents to 11 cents a kilowatt hour, and Mississippi's in that price range. But our commercial electric rates have some of the highest demand charges in the nation. It's just a weird thing. And so anyway, our demand charges are about $20 a month. And what that translates into over 12 months, $20 a month demand savings, it translates into $240 a year, you know, allowing for installation and markup. You know, that suggests that the Powerwall completely by itself in Mississippi could offer demand savings that would get it about a 6-year payback. You throw in the federal tax credit, now you're really talking about a 5-year payback or less. And so the Powerwall is actually a very great commercial product because it can deliver, you know, a 5 or 6 year payback whereas at the residential level, it's not really used for economics. Now, we were talking about demand structures earlier. You may want to take a look at the list here on the right. California, Georgia, Hawaii, Wisconsin, Alabama, Alaska, South Dakota, Wyoming, Virginia, North Carolina, and Colorado. In all of those locations, if you go to your electric rate structures on your website, you may find on your utility website, these are regions where they are allowed to have residential demand rate structures. So here we're on Ohio Power and Light's rate structures, and we can see that they have a residential demand metered service that you can opt onto. So if you're thinking about buying a Tesla Powerwall, you may want to start looking first to see if there's a residential demand rate structure available to you. And that could make the system much more cost effective. So anyway, back on lead acid, flooded lead acid will range from $90 to even more than this. At the top end, about $200 a kilowatt hour after the bid process is all said and done. I'm not a big fan of the AGM battery simply because if you're going with the AGM, you might as well go with lithium ion outside niche markets where lithium ion is not as robust for temperatures than AGM. So depending on your job site, that may be a little bit different. And sometimes it's kind of a choice of, do you want to use a quality lead acid battery and maintain that only use it for and it's only discharge it 20 to 30%, or do you want to use something that costs 5 times as much and buy a battery bank that's 5 times larger? Often lithium, anyway, I don't know, I don't think that was that clear. Let me just go to the next slide. These are kind of, I don't really know what I was trying to say there. I think I was just trying to say that it's all right to oversize your battery banks because you kind of get a proportional product life out of it. Okay, so here are some options. We have we have a Powerwall 2 that would cost us $5,500 for 13 kilowatt hours and have no maintenance or wait list with 3,200 cycles. Then we have flooded lead acid for 13 kilowatt hours that has a similar amount of cycles as the Powerwall 2, but it costs more money, $7,800 instead of $5,500. Except that this is really just a lead acid battery bank that we're only using 20% of for $7,800. So you actually have additional capacity when you need it. And the downside is it costs more and there's maintenance. So lithium ion, really once it becomes available, the Powerwall 2 at the price point Tesla has marketed, that should replace a lot of flood acid battery applications, except the off-grid market when you still need that raw storage. The real loser here is the AGM batteries that are the no maintenance. I put maintenance, it should be no maintenance. And for what's equivalent of a 13 kilowatt hour cycle, that's equivalent to flooded lead acid, you're looking at 13,000 versus 7,800. So, it's just by the time you say, well, why don't I upgrade to a no maintenance battery, you might as well just wait for the Powerwall 2 to come out. If you can't wait, then that's a good application for a starter battery. So looking at the different products that are on the market, the slide's a little blurry, but we got LG Chem. LG Chem is a Chinese company. They're kind of the largest producer of batteries right now. Then we have Tesla, and everyone's heard of them. Then there's Sonnen Battery, which is actually an Outback inverter with Sonnen's own lithium iron phosphate battery. It's kind of like the Mac or the Apple of the battery industry. It looks good. It gets good notes for being consumer friendly. As a programmer, I kind of disagree there a little bit. I like kind of open architecture systems, but anyway, so it's not smart home ready, or at least it wasn't a year ago. But what we can see is the cycle life here. We have the Tesla Powerwall and the BYD battery. They're only rated for 4,000 cycles. The Sonnen battery is rated for 10,000, and the cost, there's a huge cost difference too, and that's the cost difference between lithium ion and lithium iron phosphate. And then Mercedes has also recently come onto the U.S. market as well. So those are kind of your battery providers, but then there's also, piecing your own system together with lead acid and battery inverters. This just gives you an idea of the level of scope right now. LG Chem is the biggest battery maker on the market right now, with about 3 gigawatt hours of capacity. And, once Tesla opens up their battery factory, assuming they get that far to full capacity, and same thing with BYD that has, it's a South American company that has similar announced expansion growth like Tesla. We can see the size between 2016 and 2020 of the lithium ion production capacity increasing by, 200 times the amount what we currently, or 20 times the amount of what we currently have. So that's pretty exciting. We already talked about these concepts, so I'm going to kind of glaze through them. It's just that, I remember the era when the price of solar modules was dropping every single month for a sustained period of time. It looks like we're about to get into that with the lithium ion industry. Tesla's already reporting a cost, like a hard cost of their batteries to them, which they actually buy from Panasonic, at $190 a kilowatt hour. So their battery products actually should be pretty decently profitable. They add in an inverter and the electronics in the shell to that, but if they sell at $470 and their hard cost is of the batteries $190, the Tesla battery is a pretty good profit margin. So they actually reported a profit for the very first time right before the SolarCity acquisition. So I don't know, some investors were really happy about the SolarCity acquisition, others weren't. Let's see, I don't know much about the flow batteries other than the one company I follow, RedFlow, was announced leaving the market. There was also kind of an experimental salt battery using salt water as the electrolyte called Aquion, but they recently closed up shop. So, lithium ion and lead acid still seem like they're the kings. One of these slides are, and this is kind of interesting, over in California, up in the research and development end, they've made cathodes and anodes that can be cycled hundreds of thousands of times in laboratory conditions. So, that's what everyone's working on is, if you're going to buy a $50,000 battery, is it possible to get it so that will literally be the only battery you'll ever have to buy, rather than trying to make it cheaper, just trying to make it last longer. Okay, so we've looked at there's a few battery applications. There's energy arbitrage, where you have a lower off-peak rate and a higher on-peak rate. You charge low and you sell high. There's demand management for peak load shaving. And just looking at some of the economics, we saw at the end of our bid process, lithium ion coming in at around 14 cents a kilowatt hour. We saw the nickel iron battery coming in at around 9 cents, and lead acid coming in at around 16 cents. So for the lowest total life cycle cost of the current batteries, which is the nickel iron battery, that's not a product recommendation. We went with a different battery, but it is the lowest total life cycle cost if you exclude maintenance costs, which to some extent you can automate. But you're looking at a 9 cent a kilowatt hour battery, which means that you really need to make money off of day trading electricity, 20-cent differential between peak and off peak. And let's assume that we can use the battery perfectly efficiently. And, 1 kilowatt hour of storage is going to save us 20 cents kilowatt hour a day for 1 hour a day, 365 days a year. So that comes out to be 73 cents or $73 a year. And let's assume our all-in installation price of the system is around $800 a kilowatt hour. So there's some pretty big assumptions in here, but that's the Tesla Powerwall, the hard cost was around 470 just for the hard cost. So then you throw in labor, it's around 800 times 70% because of the tax credit divided by $73 a year of cost savings. And this battery system would have about an 8-year payback, which is about as far as most customers want to go. Now, the point of all of this was really to say that, 20 cents of cost savings each year when your battery banks are still at their current pricing, you might see an 8-year payback off of daily use. But if your time of use rate structures are only available for half the year, that takes that 8-year payback and pushes it out to 16 years. And then you say time of use metering is usually not available on the weekends. That takes that 16-year payback and pushes it out to 22 years. So it's just, energy arbitrage sounds nice. In fact, in some states, they ban you from doing it if you have net metering, where they will revoke your net metering privileges if they catch you day trading electricity with your battery bank. So it all sounds nice, but there's really no cost savings in that, or very little. You're not going to make money off of it. Let's see. This is just to say that some utilities have been starting to be a little obstructionist towards batteries. It's harder to obstruct batteries though because you're not using grid assets. So then there's peak load shaving, where you're saving at demand, and $20 a kilowatt is pretty high. Most areas it's around $10 to $14 a kilowatt. In New York City, I've seen it above this, up into $30 a kilowatt. And this is kind of exciting for the New Yorkers because they don't really have the rooftop space for solar, but they have space for at least lithium-ion batteries. And so if you got $20 a savings per month, at $800 a kilowatt, you could have a pretty good payback. But if that 1 hour of operation, if you actually need to operate for all day for the same amount of demand reduction, that battery wouldn't be very cost effective. And what I mean by that, why don't we skip ahead and look at some graph, or I guess we're here. What you really need to do for economic modeling of demand management is model your building demand for every single demand period of the day. And usually your utility will give you this demand data for commercial buildings. Sometimes it's available for residential as well. But this in dark blue is the building's old demand without solar. And then what we see in yellow is the solar array turning on. Here's a sunny day, and here's a sunny day, and here's a sunny day, and here's a cloudy day. And so we see we also see when it's the weekday versus the weekend, because now in light gray is the new power, and now here's the weekend, and the building almost goes down to exporting whenever the sun comes up. And now right here we get a little bit of export. Well, now the day comes, and now the building demand, look, instead of being sustained and flat throughout the entire day, now we get two little triangular peaks. And so for a battery, it used to be that that battery would have to run the entire day and shave off this entire load to do demand savings. And so instead, you would just have a small battery just to shave off the tip top of the peaks. And actually, that might be a very cost-effective combination, is to have the solar array do the bulk of the demand leveling throughout the day. But now, instead of just shaving off the very top peaks with your battery, you can go deeper into your load leveling and get closer and closer just to your base load and keeping everything nice and flat. Now, how deep into this demand reduction you can go, you start to get diminishing returns as these peaks get more flat rather than short, spiky, and narrow. But from a planning perspective, you may be finding that some of your clients have demands that spike way up in the morning and then are flat the rest of the day. So I've seen a demand curve that looked like that in agriculture, where they run their grain mills in the morning to feed their animals. And then that's their really only the energy intensive process for the day for the farming operation. And, they can't use solar for it because they do this at 4 a.m. So they're very excited about batteries for economic reasons. And then solar becomes kind of an add-on that you add to the battery project in order to qualify it for the tax credit. And one thing that modeling software can do with regards to the tax credit is the tax credit on your battery bank is only applicable to the portion of the battery bank that is charged by the renewable energy system. So technically, if at the end of the year you have charged your battery with 99% solar and 1% grid, technically, if you claim 30% on total system costs, you have to return the 1% that you ended up not using for renewable purpose. So you can there's a margin to which you can have the battery be charged by the grid versus renewables. But once you exceed, I think, like an 80% threshold, you can't claim the tax credit for whatever the difference is between the two. That's what you have to ratio it out. And so these are screenshots from Energy Toolbase where they are actually looking at every demand increment for the entire year and then the PV watts estimate for the entire year, and they're simulating the use of the battery bank. That's when they're charging it. Here's another charge cycle. Here's charging in the morning and in the evening. Or you could do a different mode where it says don't charge from the grid, that you only charge, and maybe you're charging right here in the middle of the day at peak, and then using the rest of your solar energy to do demand management and battery charging when you're not at the peak demand. You might also, this is using the battery every single day, but depending on how much load leveling you're doing, you might not be using the battery every single day. It really depends on your load profile. But here's what's most telling is here's a day where it's cloudy, so there's almost no solar production, and you can see the building's demand is almost up to where the building demand is on a partly cloudy day or even on a sunny day. The sunny day is only slightly higher than the partly cloudy day. So don't want to ramble on too much more about this, but essentially for commercial storage projects, you have to start using very granular modeling software to even determine what the economics are. For battery systems, there's the economics are less important. There's some optimization that it's doing, a couple of case studies that basically prove what we were just saying. I want to spend the rest of the time kind of talking about the wiring system. I'm going to grid so here's a wiring system on a typical inverter. Here's your PV DC disconnect going into, this is actually a batteryless inverter. And here's a load panel that's a critical load panel. And here's a battery inverter that's tied into the line side of the critical load panel that the solar array is also tied into. And then this is the customer's main panel and the meter box and the disconnect and then the grid. And so what happens when the power goes out, the grid goes down, this might be an automatic disconnect switch, or it might not be. There's actually on this one, the main panel goes out and the inverter itself will switch onto the critical load panel. And then in that case, the solar array still turns on and we're running as an off-grid kind of island until the power comes back on. And what I think is kind of interesting about this configuration is you could put a transfer switch right here and essentially disconnect from the grid during the day. As long as your batteries are charged and your solar array is on, so let's say you go with the same product line so we can curtail the solar power rather than turn it off, is on a sunny day, you can completely disconnect the home from the grid and just run off your solar array and your battery bank, and then as needed to charge your batteries or what have you, you can switch back onto the grid as needed. And why would you do that? Well, if utilities start really ganging up on solar owners with solar discriminatory charges, I just think it's useful to know that there are design configurations out there where you don't have to connect the array to the grid, that you can have an off-grid home kind of hybrid solution that sometimes it's off-grid, sometimes it's not off-grid. And while that might not have much pragmatic use in the United States, in other countries where they pass actually harsher penalties on connecting solar to the grid, that will help you kind of say, well, my solar array is never interconnected to the electric grid. It's only on a transfer switch, and that transfer switch is only when I'm disconnected from the grid. I'm never interconnected. I don't need an interconnection agreement, and I don't qualify for the solar fees because I'm not exporting power back onto the grid. That may or may not be wishful thinking. But anyway, just to kind of wrap things up here, some inverters you have to watch out for because they're 120 volts, and so you may need to buy a transformer to get to 240 volts. We ended up going with Schneider as our battery inverter because our charge controller was also Schneider. It just keeps things easier to have it all be the same product. So I like the Schneider solution. We went with lead acid simply for the reasons discussed. We needed the storage capacity. We went with DC coupling for reasons discussed. I've included a couple of different wiring solutions that I think kind of serve as an aid as to what's going on from like wire diagram versus what it means. So some of this stuff is kind of repetitive. This was a solar array we built for Half Moon. This is a line side disconnect before the power goes into the home coming from our ground mount inverter. We did not go with a battery inverter. We went with a SMA inverter. We have our power outlet on the side that we can plug into. And then the grand idea is that later on down the road, all we installed was this, and then the next phase of the expansion is that, and then down the road we can get rid of the grid connection. Let's see. Some different wiring diagrams, but that's pretty much it for the class, and we're out of time. So I'm going to unless there's any questions, I'm going to let you go. Now's a good time to answer questions, but or ask questions, but if you have any additional questions about batteries, if we didn't get into what you wanted to know, or if, I don't know, if there was something that you remember us covering, but you need some clarification, you can always send me an email. My email address is john@community.solar. My website is community.solar if you want to check it out. We do newsletters, and I also put my educational content onto the website. So there's stuff there. If you're a Half Moon student, create a profile. Otherwise, just send me an email. That's often the simple way to do it. And so with that, thank you for coming. We're out of time. Can't talk about everything in 3 hours, but use me as a resource. With that, I'll pass it back to Half Moon.
All right, thank you very much, Mr. Cromer. I do want to let everyone know that if you need continuing education credit for the webinar, just be sure to complete the quiz that will automatically appear on your computer screen after the webinar ends. If that does not appear for you, or if you don't have time to complete it right now, you can always access it through the thank you or follow-up email, which is sent about an hour after the webinar has ended. Thank you very much to Mr. Cromer for the presentation today. We really appreciate it. And thank you to everyone out there who has attended today. And with that, I will end the webinar and put you into your quiz. Thank you very much, and here is your quiz.